Good morning. So today's lecture will be focusing on some Schumpeterian growth models. I already have some PDFs for this purpose. So first, we're going to look at the simple model of product variety. This model, the simple version of this is was published in Journal of Political Economy in 1990 by Paul Romer. I'm covering here a very simple version of it. So this version is from Agion and Howitt's textbook, chapter 3, I suppose. So here we assume a model in continuous time. There is a household, right? So a representative household is there. So they have this isoelastic utility function. And they accumulate assets, right? So you know that the decision, the consumption saving decision of such a household is represented by this earlier equation, right? So if R is the real interest rate and rho is the time discount rate and epsilon is this preference parameter, the growth rate of consumption should satisfy this earlier equation, right? So that's the household side, and as you see, it is typical optimal growth structure that we impose on the household side of this model. Okay. Now in this model, growth will occur through the growing number of product varieties. Okay. So what are these products? Well, we assume that there are some number of machines that the firms use as intermediate inputs. Okay, so there is this MT number. So this is the measure of these machines. Okay, and there is this aggregate production function, the one that you see here. Now, this production function has labor in it. L is labor. Okay, and for that moment, we assume that L is constant. Okay, so the labor endowment of this economy is constant, or the number of workers is constant, and alpha is a parameter that determines the curvature of the technology. And this part you see is a capital aggregate. Okay, because now we are assuming that there are machines that lie between the 0 MT interval. Okay, so it's a continuum basically. So we index these machines from 0 to MT, and XIT is the units of the machine I used at instant T. Okay. So this is then an aggregate capital term, right? So this one that I highlight is an aggregate capital term. So we first take the exponent of XIT for each I. Again, I is ranging from 0 to M, and then we sum all over, right? Because this is integration. So that's the production function of the final goods sector. So there is that final good YT produced by labor and these machines. Now, for simplicity here, we're gonna look at a symmetric equilibrium. Okay, and there will be a good reason for that as well. So it is not a totally unrealistic assumption, but for the moment, just before we are solving the endogenous technology problems, just look at what happens in a symmetric equilibrium, right? So here, if there's a symmetric equilibrium in terms of the amount of machines used from each machine, we can actually arrive that measure xt of capital, right? So how do we do that? Well, the total x is defined in this way, right? Under symmetry, we have this, so xt goes out. Then whatever xt is, we're gonna determine that. But xt times mt would give you a measure of total capital. Now, if you put this back into it, right? So if you use x, little x, right? Lowercase x is equal to uppercase x divided by m. So if you put this back into the production function and do the math, you see that the production function can actually be written as a Cobb-Douglas one. Okay, as you see in here in the last step. So in a symmetric equilibrium, if you use each machine by the same amount, right? If you have that type of symmetry, then you can actually write this production function in a Cobb-Douglas way. You don't, so strictly speaking, you don't have to use, you don't have to look for a symmetric equilibrium. You can create a version where xits all differ, but in the simple version, we're gonna see symmetric equilibrium is all that we need. Okay.
How can we measure the empty intermediate goods, or in other words, machine here?
We are
Something like that.
We are just indexing them. So m is the number. You may imagine that m is just the number. Suppose that m is equal to 5, then you have 5 different machines. The interesting thing, of course, is that we are making this a continuum. So 0 mt as an interval is a part of the real line, right? So you may, in principle, have 4.2 machines as well. Okay. So for that reason, it is called a measure. Okay, it's a theoretical construct. Maybe I can show you this. Where's my screen? Okay, so if you imagine just a sec. Okay. So the idea is this. So this is, oops. So this is the real line. Let's say start at 0, right? So that goes to positive infinity. And suppose that mt is here. Now, when I define the set in this way and index the intermediate products or intermediate inputs by I, what I am assuming here is that there is an infinite number of them, right? But in the meantime, if you want to understand how much do I have, now in the symmetric equilibrium, what do you have? Empty here, so there's just one here, right? So eventually you have xt empty, right? So it gives you the summation of them, okay? So if you have, let's say, 3 machines, you can still tell me that, okay, if x is x could be anything, but suppose that x is equal to 5. So you have very simply write this. Okay, so that's the beautiful thing of using the concept of a continuum. Okay, in a discrete framework, so you can actually write a discrete version of the model as well. So if you don't like this version, you can write this, and I would be going from 1 to MT again, okay? And then you would have L, 1 minus alpha again. And you can still work with that, but working with the integral is much easier, taking the derivative, writing the totalities, etc. So for that reason, we are using that type of a continuum. Now, what would happen if m is equal to 1? That would be an interesting case, right? If m is equal to 1, the total is equal to aggregate. We also use this from time to time, okay? The per machine level would be what? In a symmetric equilibrium, that would be just xt di, so it would be equal to just xt, right? So aggregate xt, and the individual, right? This is aggregate, and this is individual. They are the same when mt is equal to 1. So this is just a device to index variable in such problems. So important concept is the measure, okay? So the measure is m, okay?
Okay, thank you. Maybe we can use world input output table for the to calculate the MT version.
You can do many stuff. If you want to take such a model to the data, you may also imagine that m is the number of firms, okay, number of different firms in the economy, because typically in such models we assume that each of these intermediate products is going to be produced by a local monopolist, as we're going to see now. Okay, but yes, input output data is particularly useful if you want to study that. There is actually a version of a growth model where there are, so the theory postulates certain input output relationships with all the intermediate products in the economy, and then you can take that model to data and use the input output data for the country you have. So there is this database called World Input Output Database. So they have this large set of data. Okay, so let me continue again by sharing my screen. Okay. So now we understand the logic of this production function. So in the final goods sector, we assume that there's perfect competition. Okay, so it's very simple. So there are firms in this sector. There could be many firms. So, but they're all identical and work with this production function. So they pay for labor. So there's a wage cost. Okay, and they also pay for the machines, right? Because they use from machine I, they use XIT units, right? XIT units of machine I, and they pay a price for that. Okay, so they purchase this machine I from the producer of this machine, and in that market, in that market of machines, they pay PIT XIT for machine I, and the total cost of machines then is the summation of this, right? So the integration of PIT XIT across I. Okay. So very simple. First of the conditions, just take the derivative. So don't be intimidated by this integral term. Integral is just summation, so you can easily take the derivative. Okay. as if it is not there, right? So if you want to take the partial derivative with respect to L, it is just you're taking the derivative, and then what you find is the inverse demand function for labor, right? So the firm's inverse demand for labor is that. And then you have this term, right? So as you see, you are just taking the derivative, okay? There's nothing confusing here because you are doing that for I, okay? You are doing that for each and every machine you are using. Okay, this must be true for this must be true for all machines, right? And then, of course, in that model, since we have intermediate products, GDP is different than output, right? So with intermediate products, GDP is just the totality of the final goods. So we subtract intermediate products from the output. Okay, so finding the inverse demand function is necessary, especially for the machines, because now we want to understand how these machines are produced. Okay, so the first sector was done. That was the final goods sector, and the behavior of the final goods sector firms are typically characterized by these first two conditions. Okay, now we have the second sector, intermediate input sector, right? So intermediate input sector is, so there are MT of them for each particular T, obviously, right? So each machine is going to be produced, and each machine here is going to be produced by a single firm, all right? So that single firm, by construction, is assumed to be the monopolist. Okay, so they have the property rights, intellectual property rights, to produce that stuff, and their profit will be written in this particular way. Okay, so what is that? The first term here is the revenue, right? So I sell XIT units to the final goods sector, and I sell at the price PIT. So PIT XIT is my total revenue. And here we are assuming that there is a one-to-one production function. Okay, so I take 1 unit of the final goods and I convert it to capital. Okay, so that may look like a very restricting assumption, but it is actually not. Why? Because if you want to accumulate capital, you always write that type of production function, right? K dot is equal to I minus delta K. Remember that equation from the Solow model. Here, we assume a similar thing, right? We make a particularly simple assumption that, so there is this output, and I can take output from one shelf, and I convert it to machine in the other shelf, right? So that's particularly simplifying, of course. Now what happens? Well, the price of the final good is equal to 1. Why? Because this is a general equilibrium model, so we want to normalize at least one goods price to unity, okay? Because we can always solve for relative prices. So then, if the price is 1, the total cost I'm paying for production of machines is just equal to Xi. Okay. Then I solve this problem as any other monopoly problem. Okay. So I know the demand curve, right? So this is the inverse demand. So I can write the revenue only as a function of my production level. Then the problem is very simple. Okay, I just want to decide. I just determine the supply of my machine, and given that supply, my the firms that demand my machine will always purchase whatever I supply because their demand curve is elastic. So I solved this problem and determined the optimal, as you see, I determined the optimal level of supply.
Can you explain the second term? Sorry, in the first equation, I didn't got it because of the connection problem.
All right, so let me do it. Let me also use my screen. Okay, so it's very simple. Now, typically you write this, right? For capital accumulation. So what do you assume here? Well, capital accumulates because you make an investment spending and there's depreciation, right? So this is investment. This is depreciation. Now, what you assume here is this. So there's output. Suppose that this is cookies. Now, output becomes investment and investment becomes capital stock, right? So there is a one-to-one relationship between output and capital, right? From output to capital, we are assuming that they are the same thing, right? So what we assume here is something similar, okay? So there is this XIT machine, okay? For production, you need XIT units of the final good, okay? So the price of the final good is normalized to 1, okay? Because this is the Numerier, okay? Because this is the general equilibrium model. Then the profit of the monopolist is this, right? 1 times XIT, because to produce XIT units of the machine I, this monopolist needs XIT units of the final good, okay?
Okay, thank you.
All right. So let me share my screen again. So then the profit is there. So again, I put the inverse demand function here. So I find the profit is a function of supply only. Then I find the optimal supply. Now realize that the optimal level of supply depends on 2 things. Oops. So it depends on 2 things. One is the parameter alpha. Remember, alpha was the production function parameter. And the other thing it depends on is the total labor demand of the final goods sector. So L here represents the size of the final goods sector. If L is big, the final goods sector is very large. Okay, this the scale of it relative to the economy. Okay, if L is small, then the sector is small. So why the number of workers matter in the final goods sector? Because if I want to serve that firm, serve that sector that is getting large and large, I need to increase my production level, right? Because there is this complementarity between labor and capital. Okay. So that's the logic. So it's I have to respond, right? So if that sector is getting large, they're more willing to pay a higher price for the same unit, higher price for the machine of the same unit. Okay. So what we learn here is that the equilibrium is symmetric. Okay, so as you see, it is not actually an assumption, it is a result. Besides, since population is constant, the optimal level of machine production is also time invariant. Okay, now using the production function and the definition of GDP, if you put these back into these definitions, and if you do the math, you realize that GDP can be expressed in this way, and this part is constant. Okay, so the number of machines and GDP are proportional. Okay, so that's an important result. And so here again, we see that how technology becomes a source of growth, right? Because if you increase the number of machines you have, if you increase the menu of machines, in that sense, if you increase the complexity of your production processes, then you can produce more. Okay, by the same number of machines, because that optimally is a constant, but the number of machines you have, the technological complexity of your production process, right? Using not just a single machine, but many machines, such as the production line in the forest system. So that's good. So we want to increase the number of machines that we use. That's the product variety model. Obviously, we want to do that. And finally, we can write the profit. Okay. And as you see, profit is also symmetric, right? Because profit is solely depending on the supply, X. And once you do the math, you get this result. Okay. So the profit level of machine producers in the intermediate goods sector is also proportional to labor. Right? So if their customers are getting larger and larger, that's good for the machine producers. Okay, so sectors are connected in that particular way. Okay, now the third sector is the research sector. Okay, so now we're going to talk about technology, right? And here the idea is this. So let me first describe the story informally, then we look at the math. So the idea is this. In this economy, there will be entrepreneurs. Okay, so some agents will be prospective entrepreneurs, and what they want to do is to invent a new machine. Okay. Now, obviously, you understand why they are incentivized, right? Because there is a profit opportunity out there. So if I create a new machine, there is always a customer there that I can serve, right? So there's a final goods sector. As long as my machine is relevant for the production, and of course I want to invent a particularly useful machine, not just a toy. Okay, so that will be useful for the production of the final good. But if I make that invention reality, then I can patent it, right? So I would have the commercial rights to produce and sell, at least for some time. Then I can serve this market to make some profit. Okay, so that's the overall idea. And there's a nice way of mathematically modeling it, and we're gonna see that after the break. So let me pause for a moment. If you have a quick question, I can answer it. or after the break, we can continue.
Can we add the import here? For example, in Turkey case, we are importing the intermediate goods, but here one sector is producing intermediate good. Can we extend the model by adding?
Yes, there are actually extensions of such models with open economy considerations. So there are intermediate goods that are exported, there are intermediate goods that are imported. You can do it. So there are models like this. Of course. So the trade and growth literature, so there's a literature called trade and growth, is getting, some models are more like growth models, some models are more like trade models. So there's a mixture there as well. Okay, so we have less than a minute. So let's meet at 10 a.m. Okay. After 20 minutes, let's meet at 10 a.m. And continue with the research sector.
Okay, thanks.
Okay.
All right, bye-bye.